Hey there, everybody. Welcome back. This is Calculus 3 at College of the Sequoias, fall of 2022. We are doing in this section 14.4, which is on surface area with parametric surfaces. So recall the formula that we had for surface areas of revolutions way back in, what was it, Calc 1? I think, no, Calc 2 maybe. We did 2 pi times f of x times the square root of 1 plus the derivative of f of x squared. We evaluated that from a to b. We integrated and evaluated from a to b. We can kick that up a notch for multivariable functions. So let's just take a look at what the multivariable function would look like. We've got some surface sigma, and it's a function of z is a function of f of x, y. That's how we got it. And so the surface, we'll call it sigma. We can break it up into small little curvy linear patches. So we're going to call each patch delta or sigma k. It's got a surface area delta sk, and it's lying above the region rk. So it turns out we can approximate. We did this with tangent planes earlier, doing a linear approximation. We can approximate the surface area of delta sk doing the rectangle that corresponds to the tangent plane at a point. So we're going to pick a point, PK. It's going to be one of the corners of the rectangles. So you can see that here. It's the corner of the rectangle on the surface patch, or the curvy linear patch. And so we want to use it. We can make this rectangle using two variables, or two, I'm sorry, not variables, vectors. One vector we're going to do where we're going to hold x constant and just do the vector in this direction. So we're going to go at distance delta yk. And that means the z component is going to shift a partial derivative of z with respect to y, then delta yk. And we're going to do the same thing for q2. We're going to hold y constant, just move in the x direction at delta xk. And so when we do dz dx, we have dzx and then delta xk. We're trying to take the function derivative of x with it, but z is a function of x. So recall we had a formula for finding the tangent plane. We're not going to use that so much. We're using these two vectors here. We don't know that it makes a nice little perfect square. It should. Well, yeah, it should. But we found that we could find the area of the parallelogram doing the norm of the cross product. So that's what we're going to do. So the way we had the patch in the other image, you can see Q2 was in this direction along X, Q1 was along Y. So N will be the normal direction pointing up. And of course, this is not necessarily pointing in Z because these were derivatives with respect to X and directs with respect to Y. So we find the cross product of Q2 cross Q1. This is from what we had, our formulas from the other page. Q1 and Q2. Okay. We're going to cross those. And when we do, we get negative, the partial of Z with respect to X times delta X, delta Y. Then the partial of Z with respect to Y, well, negative 1. Delta X, delta Y. And then Z is just delta X, delta Y. We factor out a delta X, delta Y. We've got negative dz dx, negative dz dy, and 1 times, and that's like our area. So if we take the norm of that vector, recall as we do dx and dy, these are going to go to 0. These are part of the integral. But the norm of this is going to give us dz dx squared plus dz dy squared plus 1, the square root of it. So that will be our integral. We do one small, this was the surface area for one small patch. We integrate by sending the area to 0 for each small patch. And so we get the integral. So we're going to have the double integral over R, the square root of dz dx squared plus dz dy squared plus 1 times dA. Okay, very similar to what we had before. derivative squared, and a 1. The 2 pi came from revolutions. The idea here was to make this the surface, and we're not revolving the surface. Okay? Peace. Come back with an example in a second.